When you think of a solar system, you probably imagine something like ours, a single star, a few planets, maybe a moon or two. But what if I told you there are systems out there that defy everything we think we know about the cosmos? Our journey begins close to home. The TOI 715 is a red dwarf system located about 137 light-years away, hosting TOI 715b, a super-Earth that lies within the habitable zone. This planet's mass and radius suggest a rocky composition, and its orbital proximity to its star means it's subjected to extreme stellar irradiation from frequent flares typical of red dwarfs. Given its location in the habitable zone, the atmosphere of the planet may be rich in greenhouse gases, necessary to maintain surface temperatures that could allow liquid water. Red dwarfs are notorious for violent, high-energy emissions that could strip a planet's atmosphere over time. Could TOI 715b's magnetic field shield it from such radiation? Or has the planet evolved a dense, protective atmosphere capable of retaining water vapor? By examining its spectral lines, scientists hope to detect molecules like carbon dioxide or methane, which could give clues about possible biological or geological processes. Next up, we have Kepler 90, a system so compact, it's like a miniature version of our own solar system. Kepler 90 defies the usual rules of planetary spacing with 8 planets orbiting within a range smaller than Earth's distance to the Sun. In Kepler 90's orbital resonance, planets exert a periodic gravitational tug on one another, keeping their orbit stable in the short term but possibly chaotic over longer timescales. The crowded layout raises questions about the planet's atmospheric dynamics. Are thick atmospheres even sustainable? Or do gravitational forces cause rapid atmospheric loss? Scientists speculate that closer-in planets could exhibit strong atmospheric escape mechanisms driven by extreme stellar heating, while farther planets might hold thicker hydrogen-helium atmospheres similar to mini-Neptunes, revealing how orbital mechanics shape planetary atmospheres. It's a really fascinating view, isn't it? Kepler 47, the binary star system with multiple planets. In Kepler 47, 2 stars orbit each other in a tight binary dance, while multiple planets orbit around both stars, forming circumbinary paths. This binary system presents conditions where planets might undergo eclipsing events, where one star temporarily blocks the other, causing abrupt temperature changes. Furthermore, tidal forces exerted by the binary stars could result in internal heating within these planets, similar to Jupiter's moon Io. This could enhance tectonic or volcanic activity, potentially creating transient atmospheres or even oceans of molten rock on the surface. Next, we have a truly ancient system, Kapteyn's star, estimated to be nearly twice as old as our solar system, approximately 11 billion years old. Orbiting this old red dwarf is Kapteyn b, a rocky planet with conditions that might support life. Kapteyn b's age means it has likely undergone significant atmospheric evolution, possibly starting with a hydrogen-dominated primordial atmosphere that has gradually been lost to space. Today, its composition might be rich in secondary gases like nitrogen or carbon dioxide, suggesting volcanic recycling or impacts as primary sources. Next, we have LTT 1445a. It's a triple star system where an Earth-sized planet orbits one of its stars, providing a rare setup for studying atmospheric effects under multi-star radiation sources. With 3 stars at varying distances, this system creates a complex gravitational and radiative environment. Just imagine looking up at the sky and seeing not 1, but 3 suns. The Earth-sized planet around LTT 1445a experiences constantly changing gravitational pulls from each star, which may induce eccentric orbital paths, increasing tidal stresses and internal heating. The radiation from multiple stars, each with different spectral types and luminosities, could trigger unique photochemical reactions in its atmosphere, producing exotic molecules or hazes. Now let's take a look at HR 8799. The first exoplanetary system to be directly photographed. It's a world of massive gas giants that look like something out of a dream. The gas giants in HR 8799 are young, hot, and radiate in infrared wavelengths, indicating residual heat from their formation. They likely possess dynamic weather patterns, perhaps even metallic or silicate clouds created by high-altitude condensates that form at extreme temperatures. With masses several times that of Jupiter, each planet has intense gravitational fields, likely trapping heavy elements in their atmospheres and creating pressure regimes where exotic ices or fluid metallic hydrogen could exist. By studying these atmospheres, we're on the brink of understanding cloud formation, convection, and possibly even aurorae on a super-Jovian scale. Meet Wolf 1061, a red dwarf star with a super-Earth in the habitable zone. This system is one of the closest to Earth, sitting just 14 light-years away. Wolf 1061c orbits a stable M-type red dwarf, which means its climate could be influenced by prolonged periods of stability, interspersed with stellar flares. The habitable zone proximity suggests that this planet might be tidally locked, with one hemisphere perpetually facing its star. This could create extreme temperature gradients, fostering unique atmospheric circulation patterns. If Wolf 1061c has an atmosphere, variations in cloud cover and albedo on its day side could drive intense weather cycles, while the night side may host vast ice fields. Spectroscopic studies here might reveal water vapor, methane, or other gases critical to the study of potential life-supporting conditions. Our next stop, the system Gliese 581, became famous for hosting an Earth-like planet. Or so we thought. The existence of Gliese 581g has been hotly debated, but the system remains fascinating. Scientists first thought Gliese 581g orbited in the star's habitable zone, but ongoing studies have raised doubts. It's possible that stellar activity is affecting our detection signals, making it look like there's a planet. If Gliese 581g does exist, its atmosphere would likely have to survive intense flares from the star, which could strip away lighter gases and leave a thicker carbon dioxide-rich atmosphere. This system helps scientists improve methods for spotting habitable planets, despite interference from their stars. So is there really a second Earth out there in that system? While the debate continues, Gliese 581 has inspired the search for other worlds like ours. Luyten's star is one of the few systems humanity has reached out to through radio signals. In 2017, we sent messages here, hoping for a reply from any potential intelligent life. Luyten b, the planet orbiting Luyten's star, lies in the habitable zone, where conditions could allow liquid water, a key ingredient for life as we know it. The radio messages we sent were designed to carry simple mathematical and scientific concepts, hoping to demonstrate Earth's intelligence and curiosity. Because radio waves travel at the speed of light, it'll take years to reach Luyten b, and if there's a civilization capable of replying, any response will take just as long to travel back. Beyond messaging, this star system also offers exciting science. Luyten's star is a red dwarf, which means it's dimmer than our Sun, allowing planets to orbit closely without overheating. This setup could provide stable temperatures on Luyten b, although the planet would still have to contend with stellar flares that can burst from red dwarfs. Scientists are watching for any signs of atmospheric stability here, which could reveal whether it's possible for life to develop around red dwarfs. Luyten's star not only represents a chance for interstellar communication, but also pushes the boundaries of our understanding of what kinds of star systems might support life. Among the most mysterious objects in the galaxy are rogue planets, planets that wander through space, unattached to any star. Scientists estimate there could be billions of these starless worlds drifting through the Milky Way. Unlike planets in solar systems, rogue planets travel alone in the vast darkness, and their isolation raises intriguing questions about what it means to be a planet. WISE 0855-0714 is one of the closest rogue planets to us, floating freely just 7 light-years from Earth. It's one of the coldest known objects outside our solar system, with temperatures close to those of liquid nitrogen. This extreme chill suggests it might have layers of ice or even frost clouds in its atmosphere. Rogue planets like WISE may form within star systems before being ejected by gravitational interactions, or they might emerge in isolation from swirling clouds of gas. With so many in our galaxy, these planets challenge our ideas about planetary formation. Could some of them have moons, oceans beneath icy shells, or even the potential for life in some hidden form? This lone, frozen world reveals just how much we still have to discover about the planets drifting in the galaxy's uncharted dark. These incredible solar systems reveal just how diverse and mysterious our universe truly is, from diamond planets and binary star systems to lonely rogue worlds drifting through the dark. Each of these places challenges what we thought was possible and expands our vision of what home might mean beyond Earth. Which of these solar systems surprised you the most? Let us know in the comments. And if you enjoyed this journey through the strangest corners of space, and since this project is brand new, make sure to subscribe to Space Eclipse for more cosmic discoveries. Until next time, keep looking up.